Hello all, welcome back. We got a quick question, so let's dive in. The statement reads, a point charge Q is embedded at the center of a sphere of linear dielectric material with acceptability chi-e and radius capital R. Find the electric field, the polarization, and the bound charge density rho b and sigma b. What is the total bound charge on the surface? Where is the compensating negative bound charge located? So for finding a solution, again, we want the relationship between D, E, and P. So let's use the Gauss's law equivalent for the electric displacement, where we have the contour or closed surface integral of D, and that's equal to Q free enclosed. Since it's a sphere, we know that that's just 4 pi r squared. And so we just divide that over, and we get Q over 4 pi r squared in the r hat direction. So then E is equal to 1 over epsilon D, and that's epsilon is equal to epsilon naught times 1 plus chi-e. So we just put those terms in there. Pretty quick, pretty easy. For the polarization, we have epsilon naught chi-e times the electric field. So the epsilon naughts cancel, which pretty simple, pretty quick. Moving forward, our bound charges, we need, for rho b, we need the negative divergence of P, which then we see this familiar term in the parentheses, del dot r hat over r squared, which is equal to the delta term that we found back in chapter 1. Again, this delta term is normalized with 4 pi, so the 4 pi's cancel, leaving us with a volume bound charge of negative Q times chi-e over 1 plus chi-e times the three-dimensional Dirac function. Moving forward to the surface bound charge, this is P dot r hat, but it has to be evaluated at the surface of the sphere, so that's why we have capital R squared in the denominator instead of lowercase r. And then r hat, that r hat's 1, so pretty quick, pretty easy there. The charge on the surface is the bound charge times the surface area, which is 4 pi r squared. And 4 pi r squared cancels in both, leaving us with Q times chi-e over 1 plus chi-e. Thus, the compensating negative charge has to be at the center. When we take the volume integral of the volume bound charge, we see that the negative carries from the negative divergence, and the integral of the three-dimensional Dirac is just 1. And we have a pretty quick verification that it all adds up to 0.